Okay, welcome back. Here is our last lesson in this particular series on how to figure out the chemical composition of a substance. We learned in the last one about what an empirical formula was, that idea of a simple ratio of elements to get a formula out of it. And then before that we dealt with percent composition. Well, in this particular lesson we're going to put those two together, and we're going to learn a couple of different variations on empirical formulas, some other kind of extensions of this process. Keep in mind that I'm going to teach you three extended methods of dealing with empirical formulas. The first one that I'm going to teach you with percent composition is the tested one. That's the one I'm going to require you to be able to do on this particular unit test. The second one about molecular formulas is kind of the extra credit questions on the test. It's the A-level questions. So it's optional, but it's definitely something that we do in class. It's not as important on a test, but definitely something that we use. The last one about hydrates, the third method, is more of a lab skill that we're going to be coming back to. So when we get to that part of the video, I'm going to keep going, but you can kind of mentally hang out a little bit, sort of absorb some of that information if you want to. But I'm not testing you on the hydrates part too much on this particular test. I'll ask you to identify what a hydrate is, but that's really about it. So don't have to worry about that last part in terms of the test for this particular chapter. Now, if you're watching my video and you're not in my class, then I don't know what's going on in yours. But for me, just a little bit of an aside there. So moving forward, make sure you've got your calculators, you've got your periodic tables, so that you can participate fully in the practice for this. A review. What's an empirical formula? It's a basic formula. It's the simplest ratio of elements that are present. There's some advantages and disadvantages for empirical formulas versus percent composition. Percent compositions are really easy for us to calculate, but we end up with kind of weird looking numbers. It doesn't give us a nice easy formula to interpret. Empirical formulas go one step further and at least gives us a formula to deal with, more like what we're used to looking at with chemical formulas. There's some advantages and disadvantages to this. It gives us that ratio, which is kind of nice, but the disadvantages, it's always the reduced ratio. It doesn't necessarily right off the bat give us the molecular formula, and it doesn't tell us really anything about how the elements are actually bonded to each other, how they're assembled on the inside. But again, it's that next level up, more information about it. So what I'm talking about here with the molecular formula, those two things over at the right, we've got ethene and 2-propene. Both of these are organic compounds. They're types of fuel, I guess you could think of them that way. They both have very different molecular structures. Ethene's quite a bit smaller, propane's a bit bigger, but they have the same empirical formula. So we wouldn't necessarily be able to tell them apart from an empirical formula calculation. They'd both come up with an answer, a ratio of CH2. So again, in this particular lesson, the second thing I'm going to teach you will be able to how to kind of differentiate between those. So our overall strategy for dealing with these sorts of problems, just to review, because we're dealing with formulas, we have to deal with moles. We can't just deal with straight mass because different atoms have different masses. Hydrogen's quite a bit smaller than oxygen, for example. So we have to do this sort of standardizing conversion to get them into moles first. So that's always the first part. Find out your masses of each element, convert them to moles, little molar mass, little von der fraction. The second thing is to try to see what the ratio is between the different elements that are present. Couple different ways to do that, tricks and hints and stuff like that. Sometimes you can just inspect it, just look at it, and it'll be really obvious that it's say 1 to 2 or 2 to 3 or something like that. If it's not obvious, the trick I taught you guys was to divide by the smallest number of moles. So whatever you've got, if you've got 0.33 to 0.99 or something like that, if you're not sure what the ratio is, divide each one of those numbers of moles by the smallest number of moles. And that'll help simplify it out so that one of them becomes a ratio of 1. And again, we'll take a look at that in the next screen, actually, as we do the sample problem. And then the third thing is to kind of beware of fractionals. Sometimes when we do mole ratios, we get something a little bit unusual. We don't get a nice easy 1 to 2 or 1 to 3. Maybe we get a 1 to 1.5. Or a 1 to 1.75, that would be really hard. I would never do that to you in a Chem 1 class, but it could happen. Or a 1 to 1.66, like a 1 2/3. Those are fractionals. So if we get something like that that's not really close to a whole number, like 3.99 or 5.02, if it's not really close, then there's some tricks to dealing with those fractionals, like if it's a half, 0.5, you'd multiply everything by 2, or if it's a third, 0.33, multiply everything by 3 to get those to simplify out. So just some math tricks to deal with that. So again, if you need to go review. Now is not the time. We're going to use these in the next step. Okay, so how do we go from percent composition, which is really easy for us to calculate, to an empirical formula? This is the one I'm going to be testing you on, so make sure that this is the part where you're awake, slap yourself around a little bit, like, oh yeah, she's talking now. That you're ready to go on this one. So here's an example problem with NutraSweet, and this is actually real stuff. This is the artificial sweetener that we see all the time. Less common now. There's some other ones that are a little bit better, but it's out there. It's aspartame is the other name for it, I believe. So anyway, If we have this sort of data, how can we convert from percent composition, 57.14% carbon, percent hydrogen, percent nitrogen, to empirical formulas? Because empirical formulas before, we've always done them with grams, and we've converted grams to moles. These are percents already. So here's the super easy trick. Not obvious, but super easy once you figure out what it is. If I don't tell you the number of grams in my sample, I'm going to make it easy for myself. I'm going to assume that I have exactly 100 grams. Why would I do that? Because if I use exactly a 100 gram sample, then my percents are grams. 57.14% of a 100 gram sample is 57.14 grams. 6.16% of 100 grams is 6.16. It's kind of nice. So after this, now it's pretty much easy. I'm going to take every one of those percents and I'm going to deal with them like they're grams, and I'm going to do my grams to moles conversion just like I've done. Here is my percent written as grams now, and then here is my molar mass step. So I'm going to do this out for all 4 of my different elements. So here's hydrogens, here's oxygens, oh sorry, that's nitrogens, and then last but not least, there's oxygen down at the bottom. I have a typo right here, I apologize. This should be an H, not, and I think I have those 2 backwards, that's what I did. So my apologies on these, it's going to look a little bit weird, but we'll deal with it on there. So this is the one that has to do with hydrogen, that's hydrogen's numbers. This is the one that's oxygen, because that's oxygen's numbers. So my apologies. Now we have this ratio, 4.75 to 6.1 to 0.68 to 1.7, not an obvious ratio between these guys. I can't see it, probably you can't either. So the trick, again, divide each one by the smallest number. Of these 4 mole numbers, the 0.68 right here is the smallest, so I'm going to divide every one of my 4 things by 0.68. And so here's what it looks like when I do that. See if that simplifies my formula. It looks pretty good. So what I get right here is 6.99, ooh, that rounds to 7, nice. 8.97, that rounds to 9, perfect. 680 is going to be 1 by definition. Oh, 2.5. How do I deal with that? It's one of those things I call a fractional. So right in the middle. So if I'm going to do this, here's how I would end up dealing with all that when I have a fractional like that. Because it's a half, I take my entire ratio and multiply it by 2. So I end up with an overall formula. It's big, like a lot of organic compounds. I get with a crazy number like that. 7 becomes 14, 9 becomes 18, 1 becomes 2, and 2.5 doubled becomes 5. So here's my empirical formula here. Again, I've got this written backwards. My apologies. It should be C14, H18, N2, and O5. So my apologies on that. Got myself, I don't know how I could have gotten confused, right? This isn't confusing at all. So anyway, there you go. That's the ratios that we would kind of figure out to work out on this one. Okay, moving on. How do I then go from, this is kind of part 2 of the video, by the way, how do I move from having an empirical formula to a molecular formula? Like I said back in that earlier one, ethene and propene have the same empirical formulas but different molecular formulas. So here's some examples on this screen right here of 4 different compounds that all have the exact same empirical formula. Every one of these is CH2O, but they're very, very different compounds in terms of how they act. So how do we differentiate between them? This one over here is called formaldehyde. It's kind of unpleasant. Oh, I'll go through them in order, I guess. This one over the top, lactic acid, C3H6O3. That's the one that you build up in your muscles after you exercise quite a bit. It causes muscle cramps and muscle soreness. The one on the bottom left here, there's our formaldehyde. Formaldehyde's really nasty. That's the stuff that you use to preserve dead things. Definitely not the same as lactic acid. The one in the top right up there is glucose. That's sugar. Definitely not the same thing as lactic acid. Definitely not the same thing as formaldehyde. Gross. And then last but not least, we've got acetic acid down here at the bottom. Every one of these things, acetic acid is also known as vinegar, every one of these things has the exact same empirical formula, CH2O. But they have very different molecular formulas. And the key here is that idea, because they have very different molecular formulas, they have different molar masses. The formaldehyde, the smallest one, is going to be light. Glucose, the biggest one, is going to be quite a bit heavier because it's 6 times that particular formula. So let's take a look at how this works. This next one's got a whole bunch of information on here. Don't freak out about it. So here's my 4 different compounds. They all have the same empirical formula. And so they all have the same empirical formula mass, basically a molar mass. That's the mass of 1 carbon, 2 hydrogens, and 1 oxygen added up. I get 30.03. But their molecular formulas are quite a bit different. And again, I have them from smallest to largest. There's formaldehyde, CH2O, down to glucose, which is C6H12O6. And if you take a look at this, these are all multiples of that empirical formula mass. So this is 1 CH2O, this is 2 CH2Os, this is 3 CH2Os, and this bottom one is 6 CH2Os. And just like we'd expect, we can take the mass of 1 CH2O and multiply it by that multiplier, and I get the molecular masses of each one. So there's a long way and a short way to do this. The big idea here is that molecular formulas are always some multiple of empirical formulas. Our molecular masses are also some multiple of an empirical formula mass. And that's the trick that we're going to use. If I know what the empirical formula mass is, all I have to do is figure out how many times heavier is my molecular formula, and I can figure out what my molecular formula would look like, not just my molecular mass. So here's an example of how we would use this in a problem. Okay, we've got some sort of a compound here, and I'm giving you information on it. 68.54% carbon, 8.63% hydrogen, 22.83% oxygen. We know the molecular formula, molecular weight of this thing, total weight, is 140 grams per mole. So what's the empirical formula, and then what's the molecular formula? So this is a two-part problem. You always want to start by figuring out the empirical formula and then use that with the molecular mass to figure out the molecular formula. So I'm going to work my way through this. Again, it's a good example of percent composition to empirical formula problems as well. So here's our overall strategy. Oh my God, this looks scary, but it's all the stuff that we've done. All right here, this top bullet and all the little parts to this is how to do empirical formula. No different. It's exactly the same thing as we've done before on previous slides, previous examples. Then the next part, kind of the moving forward part here, is compare that empirical formula mass to the molecular formula mass. What's the multiple? Is it 2 times heavier, 3 times heavier, 4 times heavier? Or more, I guess. And then the last part is take that multiple and you're going to kind of multiply your empirical formula up to figure out what your molecular formula is. So that's it. It's just like empirical formula problems with 2 little extra steps at the very end. So here's what this looks like numbers-wise. I'm going to do the percent composition trick and deal with it like it's 100 grams and do all of my conversions grams to moles. So here's my hydrogen, and then here's my oxygen. I noticed I did not screw it up this time. I've done it correctly. Good on me. Anyway, so here's my moles. The next thing is, as always, look for my mole ratios. So I'm going to have to divide by the smallest number because I don't see this one, 1.43 to 5.7. That's not a clear one to me. So I'm going to divide by 1.43, and then I'm going to figure out what my mole ratios are. These look pretty good. Yay, no fractionals here. So 3.99 is going to be a nice 4, 5.97 is a nice 6, and then 1 oxygen. So my empirical formula, C4H6O. Okay, no fractionals to deal with. Okay, next part. Now I've got my empirical formula, and I'm going to use that to figure out what the mass of that one thing is. So here's my empirical formula again, just to kind of clear out my screen. C4H6O. What does that thing weigh? My empirical mass for this thing is, if I take 4 hydrogens, 4 carbons, 6 hydrogens, and 1 oxygen, add them all together, I get an empirical mass, or empirical formula molecular mass, sounds crazy to say that, of 70.1 grams. Second thing is I'm going to look at the information in the problem that tells me the molecular mass, the true mass of this thing, is about 140. And I want to compare these two to each other. It turns out that my molecular mass is about twice as heavy as my empirical formula's mass. Well, that's kind of nice. I like 2's. That means my molecular formula is about twice the empirical formula. And so it would look like this. My empirical formula was C4H6O, and I'm going to multiply everything in there by 2, double it, to get C8H12O2. And if you're not sure if you did it right, go back and do the math on it. 12 times 8, 12 times 1, and then 16 times 2. Figure out what the molecular mass is. Does it add up to 140? And then you know that you're on the right track. So that's the trick for dealing with molecular formulas. Again, it's finding the empirical formula, then looking for what multiplier is it. Is it double, triple, quadruple, 6 times, I guess, and then just multiplying your formula, your empirical formula, up to get to that molecular formula. Okay, part 3. So this is the lab technique. I'm not going to test you on this, so don't panic about this part yet. It's just a variation on a theme. It turns out there's a whole class of chemicals called hydrates, and hydrates are really interesting because they end up, when they crystallize, they trap water in their chemical structure. As it's sort of solidifying. It doesn't mean that it's not dehydrated. It's perfectly dry, but those water molecules get trapped inside the crystals themselves. There's actually little spaces between the other atoms. It's kind of an interesting, weird thing that they do. To indicate that something's a hydrate, we would actually use a formula that looks like this, where we put a little dot in there. We would say it's got .2H2O or .5H2O. This one would mean that there's, for every molecule of the salt, there would be 2 molecules of water that are trapped inside, or this one would mean that there's 5 water molecules in there. And you can see this example I've got over on the right. This is copper sulfate. When copper sulfate dries, it's actually a pentahydrate. In other words, it's got 5 atoms or molecules of water for every 1 molecule of copper sulfate. When we heat it up and dry it off, We can actually really have to hit it with a burner. I mean, not just evaporating it, not crystallizing it, but literally blasting it with a torch. We can get the rest of that water to leave. And you can see that the dry salt actually looks different. It's white. That's not burning it, it's just dehydrating it. So this would be called the anhydrous salt. All that water has now been left off. It's kind of, like I said, a weird case that these hydrates do. So in terms of what this looks like, you can sort of see kind of an example of what this is. We'd have all these little molecules, and then there'd be water molecules sort of trapped inside like a cage in between these other things. Or in some cases, it's actually trapped around the outside. It just depends on the situation. So here's an example of how to do this sort of a problem. These are actually a little bit easier than the other empirical formula problems that we've done. So I'll talk about the strategy here in a second. Once you get your brain around this, it's actually a little bit simpler than the other ones. So here we've got a problem given to you where I take a hydrated nickel 2 sulfate. I had 20 grams of it. I heat it up with a blowtorch, drive off all the water. When I'm done, the dry, crusty salt has a mass of 10.37. And then the question I'm going to ask you is, what's the empirical formula of the hydrated salt? Is it a dihydrate or a trihydrate or a pentahydrate? That's the kind of question that we're looking for here. So here's our strategy. This is a little bit easier than other empirical formulas. In this one, all I need to do is figure out the moles of water versus the moles of salt. So it's kind of a more macroscopic type of an empirical formula. I don't need to know the mass of each element. I just need to know the mass of the two compounds that's present, water and then the dry salt. So this is what I'm going to do here. Is I'm going to, number one, figure out how much water did I lose, and then convert that to moles. The second thing I'm going to do is figure out how many moles of salt do I actually have. It's important to use the dry salt for this, not the hydrated salt, because the hydrated salt, all that water is still trapped in there. So we're going to calculate the moles of salt. And then I'm going to do a mole-to-mole ratio, just like we've done kind of in the other types of problems. So let's take a look at what this looks like here. So the water that I lost, when I heated it up, it went from 20 grams to 10.37 grams. That means 9.63 grams of water must have been evaporated out from there. So now I'm going to do my conversion. For the water, this is what I would get. I had 9.63 grams of water. I convert grams to moles using the molar mass of water. That means 0.534 moles of water was driven off. Now I'm going to do the same thing, but now this time I'm going to do it for the dry salt. I'm not going to do it for each element, just the salt as a whole. And that's, again, a little bit different about these hydrate problems. So I had 10.37 grams of anhydrous or dry salt. And then when I do the molar mass, there it is. That's the nickel sulfate. 1 atom of nickel, 1 atom of sulfur, 4 atoms of oxygen gives us the total molar mass of 157.75. So when I finished out this calculator, it had 0.0657 moles of salt. Now, just like I've done in my other problems, I'm going to divide. I want to know what the ratio is of these two to each other. So this is not an obvious one, so I'm going to divide by the smallest number. And so that's that 0.066. I could have done a 0.0657, it's fine. And then figure out what the ratio is. This gives us some nice even numbers here. I get a ratio of 8 to 1. In other words, I have 8 molecules of water for every 1 molecule of salt. That's what that means. So when I would write my empirical formula, they look a little bit different. We use this dot H2O kind of thing in here. But I would write it as nickel sulfate with 8 water molecules to it. We write it as dot 8H2O. And the name of this would be nickel 2 sulfate octahydrate, because there's 8 water molecules in there. Kind of crazy, right? There's a lot of water in that one. So, and anyway, that last part about the hydrates, not as important. It's like I said, it's more of a lab skill. We're going to do a lab on that. So here's the big one that you need to be able to do is this percent composition part. This is the one I'm testing you on. This is the one thing that if there's only one thing to take out of here, dealing with that simple trick that it's just dealing with percents like their masses, and it's a regular empirical formula problem from there. So there will definitely be some percent composition problems that I'm going to test you on. Second extension of this is being able to kind of scale up and go from an empirical formula to a molecular formula. Now once you found that empirical formula, once you know what that mass is, you're just trying to find a multiple of what that mass is to get to the molecular mass. Is it 2 times? Is it 3 times? Is it 4 times? And then that multiplier is what you're going to do to the formula. If the mass was 2 times as much, then the formula is twice as much. If the mass was 3 times as much, then the formula is 3 times as much. It's actually pretty straightforward. And then the last one, again, is this lab skill about dealing with hydrates. They're definitely a little bit more challenging than the other problems in some ways. You're going to just kind of see how much water got lost. I'm going to figure out how many moles of water there was versus how many moles of the dry salt there was. And I'm going to just do a similar type of a problem where it's that mole-to-mole ratio. Ratio of salt to the ratio of water. And then I'm going to write it out as a dot H2O, dot 2 hydrates, a dot trihydrate, a dot pentahydrate, tetrahydrate, whatever it is. So there you go. There is some additional ways to use empirical formulas. Empirical formulas from percent composition is the big idea I need you to have. And empirical formulas to molecular formulas is the second one. And then finally, hydrates, which is the lab that we'll take care of later on. It's really fun to deal with big torches, right? Okay. Have a good one. I hope that you got something out of this, and good luck. We'll be working with more of these in class tomorrow. Have a good night.